All right, geometry, it's been a while. Congratulations on finishing your test from the last unit. And now, since we're on flipped classroom schedule, your task is to watch this video before the next class. And now I'm getting a little more fancy. There will be questions during this video that you have to answer. It would be nice if you could print this document before you watch this video. If not, it's okay. If it won't print, I guess some people are having trouble with Macs and these equations coming from PC and that kind of thing. You notice as I get down this document, though, there'll be a question. You're supposed to answer this question during the video. If you can't print this, you'll see this question in the middle of the video, and you could just write it on a separate piece of paper. But this is basically the kind of document I used to use as the notes before in class. And I'm kind of hoping that people will get into the habit of printing this, because then in class I'll print the homework, or actually we'll probably do it from the book. But class time will be used for what you used to do at home, which was questions from the book or other assignments that I would print. Okay, so getting started with chapter 9, which I believe is our unit 8. Sorry about that. About circles and tangents. Now, you probably thought you knew everything there was to know about circles, but it gets pretty heavy if you keep going. We did talk about the definition of circle and how that definition leads to the equation of a circle. That was based on distance, because everything about circles is about a point and how far away it is from a certain center. So every point along the circle. Oh, can I do this? This would be cool. Give me a second. Yeah, let's try this. A circle, if you think about it, is every point that is the same distance from a certain center. So once I pick whatever the center is, and I pick whatever the radius is supposed to be, all the points that are that distance away from the radius, that are that radius away from the center, that distance away from the center, that sort of populates. It makes up all the points that are on that circle. And that's what our definition is. And that's how we were able to find this at. Now, this is actually from chapter 13. This was describing all the points x, y that could be any points on this circle, but it was based on that. It was based on the point x, y is a certain distance from this point in the center, h, comma, k. And this is kind of how you find that distance from h to k. Here's the horizontal distance. Here's the vertical distance. If I take that squared plus the other one squared, like I'm taking, oh, let's make it so you can kind of tell what I'm talking about. That distance squared plus that distance squared to any point on the circle, I'm going to get the radius squared. And that's why this just kind of looks like a fancy version of Pythagorean theorem. And those little red things there are horizontal and vertical. That's backwards. This is horizontal. This is vertical. Distances between the center point h, k, and any point on the circle x, y. Anyway, enough on that, because this isn't technically from chapter 13. But since I didn't test you on it already, I'm kind of thinking I'll be testing you on it in this chapter. Okay, and here we go. Let's talk about what is the circle stuff in chapter 9. Well, there's all these terms. Terms like chord, diameter, secant, and tangent, and the point of tangency. I think you've done some of this before. Well, of course, we've talked about the word tangent before. That's kind of confusing right now, because this tangent doesn't seem to have anything to do with the tangent we talked about last chapter in trig. It actually does have something to do with tangent, the tangent from trig, but this isn't going to seem like it. Also, if you continue studying trig, the word secant comes up again in trig. It's another trig ratio too. That might seem confusing when you think of it this way, but actually it all does have some relationship. I'm just going to have you do this video question now where I talk about these things. You can go back and read this, or you could pause right now and read this, but I'm going to just go through and do this sort of with you. A chord of the circle is nothing to do with music, too bad, but it doesn't have anything to do with music. Let me go back to my pen here. All right, getting this figured out. A chord is a segment of the circle, inside the circle. It has both endpoints on the circle, so something like this. This would be a chord. I'll let you do the matching thing over here. But a chord is something like C. Oh, you know what? I feel like a kindergartner today. I'll do that. The chord is something like CE. It's got both endpoints on the circle. If you extend a chord, and it goes, beyond just the part that's the secant, and it goes on and on both ways, like this. Like here's the chord, but I'm actually talking about this whole line here. That's what a secant is. So secant would be something like line AB. If I want a special chord that goes right through the center, see there's a center here at F, I have the chord, so it has to go from a point on the circle to another point on the circle. If it's the chord that goes through the center, you know about that one. It's called the diameter. So DG is the diameter. Oh, this is creative. Look at that. Okay. That's great. Well, there's only two things left. There's this thing called tangent, and there's a thing called a point of tangency. Well, by process of elimination, you could probably figure out that the point is the thing called G. So yes, that's the point of tangency. What's going on there that's so important? Well, this tangent, this AG, this line here, has the special property that it's only, oh, I missed. It's only intersecting the circle right at that one point. I'll draw another one over here so you can kind of see what I mean. I'll be a little more careful. Here comes this line, and it just barely touches the circle at one point, then it keeps going. That is called a tangent line, and this special point where it touches is called the point of tangency. All right, while I'm on the subject of tangency here, there's a thing in 9.2 actually. It's called something called a common tangent. Two circles can both be tangent to the same line. It is possible. There is a line here that, let's see if I can just hit this perfectly. Oh, I missed. Okay, well, fine. Give me a break. All right, so it's possible there could be. Oh, I missed again. Oh, can I edit that? That'd be kind of nice. It is possible. Oh, I can. Oh, can I cheat? Can I cheat? Please let me cheat. Oh, I can kind of cheat. Look at that. Okay, so there's a line here that is. Oh, I still missed a little bit. There, you can imagine there's a line that is tangent to this circle and this other circle over here later. And you know what? It's just gonna bother me just that much. I'm just gonna try to fix that. How's that? There's a line that can be tangent to both circles. You could have a line like that tangent to both circles. Oh, do I really want to open myself up for more failure? You could also have a line that's tangent to two circles kind of like this. Oh, look at that. That's pretty good. I'm going to leave that one. A line that could be tangent to two circles like that. And these lines are going to have special properties related to those circles. So anyway, when you've got a line that goes along and it hits two circles, in exactly one point. That's kind of cool. It's kind of a special thing about that line. It's called a common tangent. There's also, you can also have tangents, tangency between two circles. I could have a circle here. Sorry, I went off the screen. And I could have another circle here, and those circles could have like one point in common. That one kind of looks like the snowman version. That's the externally tangent version. But there's also an internal tangent version, which kind of looks like, okay, great, it's too big, you can't see it. If I move that, maybe you know what I'm talking about. I think maybe you already know what I'm talking about, which is that it could be that one circle touches the other circle and it's exactly right. Oh, you can't see it now. Well, that one jumped outside too. Interesting. That the point of tangency could be such that both circles kind of go the same direction, or that one circle's inside the other. That's called internally tangent circles. These are externally tangent circles, and they don't have to be the same size. They could be way different sizes. I call that the snowman when you have externally tangent circles. Also, in these two sections, they talk about spheres. Oh, I didn't bold that. Hope I don't make anybody mad here about that. Sphere is the set of all points in space that's the same distance away from a certain center. That distance is still called the radius. That point's still called the center. Things like diameter segments and tangent segments and chords and secants are still in place with spheres. But in spheres, you can get a little fancier and talk about secant planes and tangent planes and planes that intersect the circle in various ways. We're not going to talk much about spheres this year, but there's a little bit in there, and you may have heard about spheres before, so I'm going to talk about it just a little bit. The next thing, I talked about some of these already. Oh, concentric circles. Concentric circles are kind of like what they sound like. Concentric circles are, whoops, didn't mean for that to all come back. Let me get this. Okay. Concentric circles are circles that share the same center. So we have one center point, and then I might have a circle like this, and then I have okay, that's the center, believe me. And then I have another circle that has the same center. And you could have, 4 or 5 or 6. You could have a whole bunch of circles that have that same center. That means they share. Con means with. Circles that share the same center. Polygons inscribed in a circle, or circles that are circumscribed about the polygon. And then notice I have the whole same thing here, but the terms are just backwards. In this first version, I'm talking about a polygon inscribed in a circle. So there's a circle, and then there might be some polygon inscribed in it. Some random thing, looks kind of like a trapezoid. That's where I could say this polygon is inscribed in this circle, or I could say that this circle is circumscribed about the polygon. Same thing can happen the other way. Oh, the special thing about that is all these 4 corner points are exactly on the circle. And that doesn't happen with every polygon, so it's kind of a special thing when something gets to be inscribed in a circle. Circle inscribed in a polygon, this is even weirder. Say you have some circle, it's kind of hard to draw this small. some circle, then you have all these segments of the polygon, and they happen to be tangent to the circle. That's tangent. You can say that there's a circle inscribed in that polygon, or that the polygon is circumscribed around the circle. Again, that doesn't happen to every polygon. So polygons are kind of special if they make it to any one of those categories. These terms can mean the same thing, whether I'm talking about them here or here. It's just that the inscribed thing is on the inside and the circumscribed thing is on the outside. So here the polygon's inscribed and here the circle is inscribed. All right, and then, oh, notice my words aren't moving. Let me take care of that. Okay, I know this is a little bit out of order, but since we just talked about this issue, let's jump to video question 3, which is about different polygons and whether or not you think that there'll be an inscribed or a circumscribed circle that exists. Squares, as you know, are really friendly. They play nice with circles too, like they do with all the other quadrilaterals. So yeah, you could get an inscribed circle on a square. I bet you could probably imagine that. I don't know if I could actually draw it here. It'd be really small if I tried to draw this. If I want to know, is there an inscribed circle on a square? Yeah, I could perfectly get a square to fit right around that circle. And I could also get, that's a yes, I could also get a circle to fit perfectly around a square. That would work out pretty nicely. It also works with equilateral triangles. Yeah, there's a circle that would go right around there. And if I had a triangle, I could get a circle to fit. Oh, did I do that backwards? No. I could get a circle to fit perfectly inside that, tangent to all 3 sides. Yeah, the equilateral stuff is kind of nice. So from that, you might guess that, yes, these are true also. If you had a regular polygon, say you had a regular pentagon, you could get a circle to fit perfectly inside there. If I could draw a regular pentagon. Man, this is probably the smallest regular pentagon I've ever tried to draw. Or if I had a circle, I could just connect equally spaced dots around that. That's not really looking equally spaced, but you can imagine that there could be a perfect regular polygon inside there. Rectangles are a little bit harder to deal with. Do you think you could get a circle to hit all 4 sides of any rectangle? Well, I'll let you think about that. Is there a circle that's going to hit all those sides perfectly? Well, I doubt it. If I started a circle here and I had to hit the bottom, there's no way it's going to hit the sides, so this is no. And the other one is, if I have a circle, could I get some rectangle that's not a square? I mean, you know, not a square. In general, can I get a circle to fit around any rectangle? If I have any old rectangle like this, am I going to get a circle that fits around all 4 corners? Well, it turns out that yes, you are. That's a little bit harder to imagine. I think I want to leave some of these as mystery. I only have about 2 minutes left in this video. We might talk about isosceles, trapezoid, and rhombus in class. Okay. All right, so sorry I'm jumping around so much on this. I've scrolled up a little bit here. Back to the last few things I haven't talked about yet, which is the theorems in 9.2. Tangent radius theorem, this is kind of a big deal. If you have a line tangent to a circle, well, that right there, that point of tangency, is going to be the end of a radius. And there's something special about that radius with that tangent. Guess what? They're perpendicular. And you may have known that. I'm not sure. The converse is also true, which is saying if you've got a radius of a circle and you construct the perpendicular at that endpoint, you're going to hit a tangent line. You will have constructed the tangent line. So if I ever asked you to construct a tangent, that's how you do it. You make a radius, and at the end of that radius, you make a perpendicular through that point at the end of that segment, which you can always do. Sort of forget the circles there for a second. Just make a perpendicular, and that perpendicular will turn out to be tangent to the circle, meaning it only intersects the circle in that point. The circle will wrap around there and not cross the line anywhere else. And then one last thing here. If 2 tangents, and you're going to draw the same thing down here, if there's a circle with 2 tangents that come off it, some crazy tangent, oh, that's supposed to be straight, and some other tangent like this, wherever they intersect, that point right there is equal distance to the point of tangency. We'd say that the tangent is really just a segment like A to B and C to B. Those little things are congruent. AB equals CB here. Now we could talk about why that is. There's a proof in the homework, I believe. I call that the ice cream cone, because if you were just to draw the part here that we care about, I've kind of got this isosceles looking triangle. Well, I know it's isosceles, right? At the end of the theorem, those are congruent. And the circle kind of sits in there perfectly like that. Anybody else thinking ice cream cone at this point? Okay, now that you're all got a sweet tooth, I'll see you in class.